All right, so now we'll take a look at one of the other gas laws, and probably the one that is the most important one, because it tends to incorporate all of the different variables that we've discussed so far with respect to gases. And this gas law is known as the ideal gas law. And this one is going to have all the variables embedded in it. And it actually contains all of the other gas laws. If we know how to manipulate the equation, we can derive Boyle's law, Charles' law, the combined gas law, etc. So the ideal gas law is as follows. So if we take the product of the pressure and the volume, that will be equal to the product of N, the number of moles, times R, which is a gas constant, times the temperature in Kelvin. All right, so this is, again, probably the most important gas law we'll see, PV equals nRT. Sometimes people pronounce it as Pervnert, although it's not spelled that way. That's a little, will help, something to help you remember what it actually is. So PV equals nRT. So again, pressure, volume. Let's define these. So this is our pressure. We've seen this before. Volume, V is volume. N here is the amount, usually number of moles of something. R is the gas constant. Okay, and we've seen constants before. Come back to that in a second. And then T obviously is the temperature. Going back to the gas constant. So as with all the other constants, this means that whatever that number is doesn't change. So that is what defines it as being constant. And there are a couple different ways, a couple different numbers that can be used depending on the units that are being used in the other places in the equation. But typically this is 0.0821 liter times atmosphere per mole times Kelvin, right? So right away, if we're using this value for our gas constant, we know that the volume in our equation needs to be in liters, pressure needs to be in atmospheres, amount needs to be in moles, and then our temperature needs to be in Kelvin. There are other units of the gas constant that you will see, but this is the most common one that we're going to encounter. So as with any other equation, we can rearrange this. So it can be rearranged to solve for any unknown in that equation. All right, so for example, we can solve that equation for, let's say, N, the number of moles, right? So if I have my PV equals N times R times T, solving for N means I need to isolate N on one side of the equation. So N is on the right side. I need to get rid of the R times and the T. Because all of these are multiplied by each other on the right side, I can just divide the right side by R times T. So they can cancel. This being an equation, whatever I do to one side, I need to do to the other side. So I end up dividing the other side by RT. So then this gives N equals PV over RT. Okay, and this is just a algebraic manipulation. It's not the most complicated type of algebra that you've seen in our course so far, but it is something that that you need to be able to do to solve questions that involve the ideal gas law. All right, so let's take a look at an example of a question or two that will tell us where we'll be using the ideal gas law. All right, so here we have an example of a question. And again, as we've seen with the gas laws, in a lot of cases, you're not being told which gas law to use. You kind of have to figure that out from the information that you're given in the problem, right? So the best way to do this is to list what you are provided with. So for example, if in this question it says a sample of helium gas, right away we know it's helium, He, and it gives us a volume of 2.5 liters. We know V is 2.5, and then it tells us a pressure of 0.75 atm. So we know that P equals 0.75 atm, which is atmospheres. And we need to calculate the amount of helium, both in moles and in grams. So we need amount, okay, which is N in our abbreviations. And then we're also told, even though we're not told it's the temperature, we're given a unit of temperature. So T here is 15 degrees Celsius. And as we know with the gas, when it comes to gases, you want to make sure that you convert this to Kelvin right away. Okay, then we're just going to add 273 to this to go from Celsius to Kelvin. So this gives 288 Kelvin. And what we need to find again is the amount N. So we're given P, V, and T, and we need to find N. So those are all four of the gas variables that we talked about. So in this case, since we're given all of these, we're going to use PV equals N times R times T. We need to solve this for N, and we did this previously. So N, we said, rearranging the equation would be equal to P times V divided by RT. And we should have all of these. You should be given, or we should be able to calculate all of these. So we can substitute into this equation, right? So we've identified all of these. We have our volume, 2.5 liters. We have our pressure, 0.75 atmospheres. We have our temperature in Kelvin. And then R, remember a gas constant, doesn't change. And that's 0.0821 liter times atmosphere per mole times Kelvin, right? And these are the units that match up with the units that we have over here. So we can go ahead and substitute our values into that equation. And then all it becomes is a math problem. Okay, and as you've seen from the start of this semester to now, there's a lot of math involved in not just in chemistry, but in physics as well. We're not going to get very deep into it in our class, but we need to be able to apply some basic math principles to these situations. So here we have our N. So this essentially becomes sort of like what's called a plug and chug. So we're going to be plugging in our values in here and using our calculator to use. So N here is equal to the pressure, so 0.75 atmospheres. I like to put my units in so I can see if they cancel out. That confirms whether I did the algebra properly. V volume is 2.5 liters over R, so that's 0.0821 liter times atmosphere per mole times Kelvin. And T, our temperature, is 288 Kelvin. Okay, so looking at my units, I can see that atmospheres cancels here, liters cancels there, Kelvin cancels here. And all I'm left with is mole. So this is 1 over mole in the denominator. And then we have 1 on top. So 1 over mole gives me moles as my unit. And that makes sense because that's what I'm trying to find up here. And this would be moles of helium, remember, right? That's what that's the gas that we're looking at. So plugging in our values, you have 0.75 times 0.25. I'm sorry, 2.5. Try that again. 0.75 times 2.5 divided by 0.821. That divided by 288. And that's going to give me 0.079 moles of helium. All right, so that's the first part of the problem. So we have 0.079 moles of HE. And then we also need to find, so we just found the amount in moles. We also need to find the amount in grams. So we just calculated moles of helium. Now we want to go to grams of HE. And this is something that we did a few weeks ago. Going from moles to grams or grams to moles, we're going to use the molar mass of that thing, which we can look up on the periodic table. So I have 0.079 moles of helium. That goes over 1. And then for every mole of HE, according to a periodic table, that's 4.003 grams of HE. So moles cancel. So I end up multiplying then 0.079 times 4.003, and that gives 0.31. We'll round that to 2 sig figs, 0.32 grams of helium. All right, so the ideal gas law, PV equals nRT, we want to use that one when we're given all of the variables. And we just have one of them that we either need to calculate or that we need to find. So the information provided in the question will dictate which of the gas laws will be most applicable, depending on what you need to find. All right, let's take a look at another example, and we'll kind of tie in some of the previous concepts to this. So one thing that we talked about before is this idea of the molar volume of a gas. Okay, and as the name suggests, the molar volume is the volume of 1 mole. And according to this principle, to this concept, the volume of 1 mole of any gas, it doesn't matter what that gas is, it could be helium, carbon dioxide, doesn't matter. So volume of 1 mole of any gas under what's known as standard temperature and pressure conditions which we abbreviate as STP, will always occupy the same volume. And that volume is 22.4 liters, right? So that is the volume that a mole, 1 mole of any gas, under these conditions, that's the volume that it will occupy. So what is the standard temperature and pressure? Well, standard temperature is 0 degrees Celsius, which is the same as 273 Kelvin. And then standard pressure is 1 atmosphere, which is the same as 760 millimeters of mercury or 760 torr. And then there are other pressure units that it's equivalent to. But these are the conditions that we are referring to when we talk about STP conditions, right? So this is saying that under these conditions, 1 mole of the gas has a volume of 22.4 liters, and we'll specify here at STP conditions. All right, so we can use that information to do some calculations as well to interpret what we're being provided with. So let's take a look at another example. All right, here we have another example. So we're told a sample of carbon dioxide gas. So remember, carbon dioxide is CO2, and that occupies a volume of 3.25 liters. All right, so we're given, again, with any of these questions, you want to list or write down the information that you're provided with. So we have a volume here, V, of 3.25 liters. And the key thing in this question is that it tells you that it's under STP conditions, right? So in most cases, there are little clues in the question that you can look at that it will sort of lead you to the right or to the most appropriate relationship or equation that you need to use. So the fact that it's telling us STP conditions is our clue here that we might need to use the molar volume relationship, which says that 1 mole of any gas, in this case, it's carbon dioxide, occupies a volume of 22.4 liters, right? So again, it doesn't matter what the identity of the gas is. If it's under these conditions and you have a mole of it, it will occupy 22.4 liters. So you have a sample of CO2 and it occupies a volume of 3.25 liters under these conditions. And then we're asked how many moles, how many grams of CO2 are present. Well, we're given volume here. We're given also STP conditions, okay, which implies that we're probably going to have to use that relationship. And then what we need is the amount, okay, both in moles, and then we also need the amount in grams. So what relates the moles, the thing that we want, to the volume, the thing that we're given, is the molar volume under these conditions, right? So we can use this like any other relationship to help us get from one point to the other. So I have my 3.25 liters of CO2, put that over 1. I'm going to take my molar volume relationship, insert that as a conversion factor. If I want to end up with moles, the moles of CO2 go on top. So 1 mole of CO2. And if I have a mole of it, it'll occupy 22.4 liters. Now, obviously, I don't have a mole. I'm sorry, I don't have 22.4. I'm told that I have 3.25. So that's why we're dividing here by the molar volume. So this is going to give me 3.25 divided by 22.4. So that gives 0.145 moles of carbon dioxide. All right, and that should make sense. You know, just intuitively, 1 mole will occupy 22.4 liters. Well, if the volume occupied is a lot less than 22.4, so 3.25 is less than 22.4, then the number of moles should be less than 1 as well, right? And the answer does make sense. It's in the right ballpark. So that's the first thing. We got the amount in moles. We also need the amount in grams. So now we want to go from moles of CO2 to grams of CO2. How do we go from moles to grams? Well, we're going to use the molar mass of carbon dioxide. Okay, and that's something we can find from the periodic table. Look up the individual molar masses for carbon and 2 oxygen, so 1 mole of CO2. So carbon is 12, oxygen is 16. So that gives, we add them all together, we get 44.01 grams of CO2. So I have 0.145 moles of carbon dioxide. And then my molar mass as the conversion factor goes in here. I want to end up with grams, so that goes on top, 44.01 grams of CO2 for every 1 mole of CO2 on the bottom. Moles go away. So 0.145 times 44.01, and that gives 6.38 grams of carbon dioxide. So we can use, in this case, the molar volume. As long as we're under STP conditions, you can use that relationship, right? And that relates moles to volume. And if you wanted to, we can convert moles to other units like grams, depending on what the question is asking for.